Welcome back, everyone. Today, we're diving into an explainer on something that honestly sounds completely impossible at first glance. We're going to look at the engineered architecture needed to generate off-grid cold and, get this, even solid ice right in the middle of the sweltering Texas heat, totally disconnected from the power grid. Our focus today is to walk you through this absolutely brilliant sequence of passive cooling, literally flowing step by step from a towering condensation structure all the way down to an agricultural garden. So, what's the central mystery we're unraveling here? How do you cool a Texas town and generate ice without using a single watt of electricity? I mean, when we think of the Texas Gulf Coast, we immediately think of oppressive humidity, intense solar radiation, and those relentless hot breezes. Normal mechanical AC grids just buckle under that kind of load. But what if the actual solution isn't about generating more power, but just changing where the heat goes? Okay, let's dive into this. To beat the Texas heat, we actually have to look up. Way, way up. Deep space is literally our ultimate massive thermodynamic heat sink. It sits at a freezing 3 Kelvin. That's about minus 454 degrees Fahrenheit. Now, heat naturally wants to flow from warmer objects to cooler ones, right? The only catch is that Earth's atmosphere traps most of our thermal radiation. It kind of acts like a giant invisible blanket. But there's a loophole in that blanket. And this brings us to the core concept, passive radiative cooling. See, the atmosphere has this specific optically transparent band between 8 and 13 micrometers. We call this the atmospheric window. By using highly specialized materials like quartz and phase change crystals, we can basically build a high-tech one-way mirror. It reflects over 95% of direct sunlight, while simultaneously shooting thermal energy straight out of that atmospheric window and into deep space. It is quite literally dumping ambient heat directly into the cosmos. Now, you might be wondering, why is this such a challenge in Texas specifically? Well, high humidity means water vapor is partially blocking that open window. Plus, those hot ambient breezes are constantly trying to blow the heat right back in. But if we engineer an enclosed microclimate, using low emissivity windbreaks and sinking the ground grade to trap heavy, cool air, we can totally counter that harsh Gulf Coast weather. We suppress those heat index spikes and can actually drop the internal effective temperature by 10 to 18 degrees Fahrenheit. That creates a completely autonomous, super comfortable human zone. So the really crucial part is figuring out how we scale this up into a community-wide system. We're going to physically follow the flow of gravity downhill, tracking the thermodynamics through 4 distinct stages. We'll start high up at a 30-meter elevated tower, drop down into a subterranean vault, flow right through some mid-slope residential nodes, and finally end up at the agricultural drip lines. Step 1. The 30-meter cooling tower. Let's start right at the top. The highest elevation anchors our central hub. Covered by that photonic crystal sky canopy, this tower essentially strips humidity from the ambient air and cools it down. But, more importantly, being 30 meters high builds a massive hydrostatic pressure head of 294 kilopascals right at the base. To put that into perspective, if you wanted to chill water using a standard Joule-Thomson valve, which forces water through a tiny hole, you'd need a massive 6,000 kilopascals of pressure. That means you need a 600-meter tower, which is just completely impractical. But a turbo expander, that's basically spinning a tiny turbine to extract heat. And it only needs a tiny pressure drop of 25 kilopascals. So our 30-meter tower provides more than 10 times the required pressure. It's an absolute engineering marvel. Step 2. The subterranean ice vault. Heading directly beneath the central hub and down into the vault, that rapid fluid expansion through our micro-turbo expander extracts a massive amount of thermal energy. It drives the temperature from 15 degrees Celsius all the way down to -5. Down here, the system pulls out so much heat that it hits what engineers call latent heat removal. In plain English, it flash freezes the harvested atmospheric water right onto vertical stainless steel plates. Gravity chutes then drop these 10-kilogram ice blocks straight into a community kiosk for residents. Meanwhile, the leftover liquid is banked in a sump. That gives us a steady, reliable supply of heavy 4 degrees Celsius water, which is perfectly chilled for the next step of our journey. Step 3. Hydronic homes and labs. Following that chilled 4-degree meltwater straight out of the vault, gravity pulls it downhill through a closed-loop hydronic network, right to our mid-slope residential cluster and research labs, where it flows through pipes embedded directly into the foundation slabs. Now, I know what you're thinking. Running 4-degree water through foundation pipes in humid Texas sounds like a recipe for a sweating, soaking wet floor, right? But there's a rigorous, synchronized valve matrix that completely prevents that. First up, a pressure valve. PRV 101 regulates the raw tower pressure down to a safe 150 kilopascals. Then a dynamic flow valve, PICV 202, makes sure every home gets equal cooling no matter where they sit on the hill. But TCV 201 is the real game changer. It blends that freezing supply water with warmer return water to hit a perfect 12 degrees Celsius target, keeping it safely above the indoor dew point. And just in case, there's an emergency failsafe solenoid that shuts the whole loop down if floor sensors detect humidity crossing 65%. It's genuinely awe-inspiring when you think about it. Thanks to that synchronized symphony of valves, a completely passive system delivers incredible micro-scale human comfort. The research lab gets precise, vibration-free climate control, locked in at 18 degrees Celsius. Meanwhile, the downhill homes enjoy a perfectly comfortable 21 degrees. And the best part? It's all achieved through silent, radiant cooling from the floors, paired with perfectly dried, chilled, downdraft air ducted straight in from the central tower shaft. Step 4. The permaculture garden outflow. After absorbing ambient heat from the homes and labs, the water finally arrives at the lowest elevation of our journey. It exits warmed to a perfectly safe 16 to 18 degrees Celsius. That temp is ideal because it feeds seamlessly into low-pressure agricultural drip lines for fruit trees and crops with absolutely zero thermal shock. And to keep the whole pristine system perfectly safe, a back pressure valve maintains 50 kilopascals of pressure on the return line. That way, the high-elevation homes don't lose their water charge. On top of that, physical air gap preventers guarantee that absolutely no dirty agricultural soil water can ever siphon backward up the hill into the clean cooling loops. Which brings us to a final thought for today's explainer. We just tracked a completely self-sustaining thermal infrastructure. We went from a sky-facing photonic canopy down a 30-meter tower generating ice, radiating through home slabs, and finally watering an orchard, all without relying on a mechanical power grid. We already have the material science. We have the fluid dynamics. So the question to leave you with is this. Why isn't this gravity-fed, zero-power cooling technology being built in every single hot, humid climate today? Think about that as you consider the future of how we live on a warming planet. Thanks for joining me, and stay curious.